Hello everyone, and welcome to the most complex thing we'll do possibly all this year, but definitely within this unit, which is to look at some fairly complex examples of static equilibrium. We're going to do two examples here. So in the first case, we have a hinge, which is attached to a 3-meter long pole, which has a mass of 31 kilograms. The other end of the pole is held by a rope, which happens to be at 37 degrees. And I want to know, what is the tension in that rope? Well, as with all force-torque problems, we're going to start out by drawing an extended force diagram of the pole. So what forces act on the pole? Well, of course, gravity. Where would it act from? The center of gravity, which would be right in the center of the pole. The string would act on the end of the pole, and it would, of course, be at 37 degrees. And then the hinge would act on the pole. Now, this one's a little hard. So think about it from the hinge perspective. And if you think about this pole, it's going to be pushing in to the wall and down on the wall, in and down. So if the pole pushes in and down on the wall, or the hinge, then the hinge will push in and up on the pole. With me there? The pole pushes in and down on the hinge, so the hinge pushes, the pole pushes out into the wall and down on the hinge. And so the hinge pushes in and up on the pole. Now remember, on an AP test, we need to draw all these without components. Right? So you would get probably 3 points for drawing this force diagram right here. 1 point for each force. Right? Force from the hinge, and we don't really know what angle that is at this point. We don't really know much about that other than it's there. Force of gravity, and then our force of tension at 37 degrees. Now, we could draw this with components. Again, they won't want you to do that on the actual AP test, but they usually say if you need to draw it later, go ahead and draw it. So let's go ahead and draw our force of gravity, which is vertical, our force of tension, which we can then break up into F of Tx and F of Ty. So that's how much of the force of tension is to the left and how much is up. Likewise, we can break the hinge up into F of Hx and F of Hy. Now really the hinge is there, but I'm going to leave them like this for reasons which will become apparent in a moment here. I could move this one out here and draw the force of the hinge, but I want to show them both acting on the hinge. I hope you're okay with this extended force diagram. Again, this is the one they would want on the test. This is the one that it makes it easier to analyze. So, we can now write several equations. This pole is in static equilibrium. Hence, the net force and the net torque are both 0. Now, in terms of forces, we can break the forces up into horizontal and vertical. So horizontally, there's just two forces, F of Hx and F of Tx, and therefore they must be balanced, right, since it's not accelerating horizontally. F of Tx could be written as F of T cosine of the angle, since it's the adjacent side. But then we run into a problem. While we want to know the force of tension, we don't know F of Hx. So we kind of have two unknowns in this equation. So it's a nice equation. It's just not one that we can use. But say maybe if I gave you the force of tension, you'd be able to figure out something about the hinge. Now we can also sum the vertical forces. And notice that we have 3. We have gravity, of course, acting down. And we have the vertical part of the tension and the vertical part of the hinge. They both act upward. So those two upward forces have to balance out the one downward force because it's not accelerating vertically. Okay with this one? This is a Newton's first law kind of equation back many units ago. Break everything up here. Let's solve for F of Hy. Okay, we have to move this to the other side, subtract it, and F of Ty is F of T sine of 37, and of course F of G is mg, and we run into a problem. Here's our F of T that we want to find. We do know m, and we know g, but we don't know F of Hy because we weren't told anything about the hinge. So again, an equation, just not a useful one in this case. Now thankfully, we don't just have to deal with the net force being 0, the net torque is also 0. And you might remember from some of our earlier worksheets that when we're in static equilibrium, we actually can choose any point we want to sum the torques around. And the net torque around any point we want has to be 0. So there's kind of 3 points we might use. We might use this end, we might use the center, or we might use that end. Now there's actually one here that's going to be better than the others. Okay? First of all, we don't want to put it here Because if we put it at the right end, then the force of tension, which is what we're trying to find, drops out of the problem. Because forces that act through the axis of rotation exert no torque. On the other hand, we don't know either of these. So, if we decide to use the fact that the net torque is 0 around that axis, that will eliminate the torques by the hinge, and therefore eliminate these two forces out of our torque analysis, and then we won't have too many unknowns. You with me there? So we're choosing what point to sum the torques around, and we're going to choose a point that eliminates forces that we don't want to deal with, because any force that acts through the axis of rotation exerts no torque. This leaves then only two torques: the torque by the force of gravity, which technically would be negative because it would be clockwise, and the torque due to the force of tension, which would be positive because it's counterclockwise. And those two torques would of course have to balance because the net torque is 0. Okay, so everybody okay with this one? Again, notice the hinge drops right out of the problem. That's why we choose the axis of rotation to be here. Now let's do the math. Each torque is of course lever arm times force. So for the force of gravity, the lever arm is half the length of the rod. I mean, I could put in a number here, but I'm just going to call it 1/2 L. And the force of gravity is mg. I'm kind of skipping some steps here. On the other hand, the force of tension is L away. And I could put F of t sine of the angle, but let's use the perpendicular part of the force. Right? So if L is here, then F of ty is the part of F of t that's perpendicular. So it's L times F of ty. You okay with the geometry there? Yes, we could write it as, cancel the L's out. Right? F of ty can be written as F of t sine of 37 degrees. That works too. So if you want to write it as L F of t sine of 37, you'd be fine there. Solve for F of t, plug the numbers in, and we have an answer. The force of tension is about 250 newtons. And notice from our previous work that once we know that, we could go back and figure out what's going on with the hinge. We could go back to here and figure out what the y component of the force from the hinge is, and we could go back to here and figure out what the x component is. So when you're summing forces and torques in a question of static equilibrium, you often can write at least 3 equations. You can sum the forces horizontally, and it's got to be 0. You can sum the forces vertically, and the net force has to be 0. And you can sum the torques, and the net torque has to be 0. And when summing the torques, you can choose the point around which to sum the torques, which sometimes will eliminate forces you don't want to deal with. Example number 1. Example number 2. This is kind of a classic problem. You've got a ladder leaning against a wall. We're going to say the ladder has a length L, technically 15 meters. The mass of the ladder is 50 kilograms. The top of the ladder is about 11 meters above the ground. I'm calling that H. The bottom of the ladder is about 10.2 meters from the wall. Okay, so we know this side, we know this side, we know that side. It does make a little right triangle if you were trying to do some trig. Now this ladder is bottom heavy. A lot of ladders are bottom heavy. All right, they're bottom heavy because it makes them balance better. So the center of mass of this ladder is 1/3 of the way up. That's what that dot is. It's not in the center. Okay, it's 1/3 of the way up. Assume that the wall, but not the ground, is frictionless. That may seem strange, but let's say it's a smooth wall, but not a smooth floor. We can't have a frictionless floor, otherwise this would slip and it would never stay put. Right? So we've got to have some friction with the floor. So first of all, let's draw ourselves an extended force diagram, which will allow us to see all of the forces that are acting on the ladder. First of all, we have a force of gravity. Where would that force of gravity act? It would act at the center of gravity, which is where the center of mass would be. So right there. Not in the center, because it's bottom heavy. Okay? So the ladder's a little heavier on the bottom, so there's the force of gravity. Now, the floor is supporting the ladder right here. So there's a force. Technically, this is a normal force, but I want to distinguish between this one and the one from the wall. So I'm going to call it F of ground. I know that's a little more writing, but it's a support force from the, a normal force, if you will, from the ground. The wall is going to push in, right, to the ladder. That's, again, a normal force, but I'm going to call it F of wall. And there's got to be something keeping the bottom of the ladder from slipping out. And what would keep it from slipping out? Friction. So friction will act in. You with me there? The tendency is for the ladder to slip outward, so friction would act inward. And it's static friction, to be technical, because it's not actually moving. If it was sliding, right, then it would be kinetic friction. So there we go. There's our extended force diagram. Pretty complex one, although at least here we don't have any angles like we did in the last problem. Everything's nice and horizontal and vertical, so that's going to make life a little easier. So we're trying to find the forces from the ground and the forces from the wall. Well, as we said in the last problem, it's in static equilibrium, so that means the force, the net force has to be 0, and the net torque has to be 0. So let's start with the force equations. Since the vertical net force has to be 0, and the horizontal net force has to be 0, sorry, let's start with the horizontal here, the force from the wall has got to balance out the force of static friction. So, if we could calculate static friction, we could calculate the force from the wall and we'd have half the problem done. Fortunately, we can't do that. Right? Why can't we calculate the force of static friction? Well, there's really two reasons. First of all, we weren't given enough in the problem. In order to calculate the force of static friction, we would need to know the coefficient of static friction, mu sub s, right? The coefficient that's because of the roughness of the ladder in the ground, right? The types of surfaces, and we weren't given that in the problem. But even if we were, we still couldn't do it. Why? This part's really kind of a fine point, so listen carefully to this one. Okay? Remember, this is the equation for static friction. Static friction doesn't just have one value. It has a range of values. It goes anywhere from 0 to a maximum of mu s times the normal force. So the only time the force of static friction can be calculated with mu s times the normal force is if you're talking about the maximum amount of static friction. This, in other words, needs to be what we call in physics a boundary condition problem. So maybe you're saying the ladder is at the biggest angle, and if it's just about to slip out, then it would be a maximum amount of static friction, and then you could use this equation. But there's nothing in the problem that says that this is a boundary condition problem. I mean, we might be able to tilt this ladder a lot more before it would slip. Right? So in this case, we don't know mu s, but even if we knew it, we wouldn't be able to use it in this problem. Doesn't mean you won't do boundary condition problems here, but in this case, we have too many unknowns to figure this out, so this equation isn't very useful for now. Now, on the other hand, since the vertical forces have to cancel, since it's not accelerating vertically, the force from the ground has got to balance out the force of gravity. And we can calculate the force of gravity on the ladder. It's our old friend, mass times gravitational field strength. Plug our numbers in, and we get a nice 490 newtons. And there's half the problem. So sometimes just analyzing the forces is enough. We don't always have to analyze the torques. Sometimes the forces will work. However, since we couldn't figure out from the wall, we've exhausted our force analysis, so now let's analyze the torques. Again, it's in static equilibrium, so the net torque must be 0. And we can therefore choose anywhere we want to sum the torques around. So we might choose up here by the wall, but if we did that, that would get rid of the force from the wall. It wouldn't exert a torque, and that's what we're trying to find. We could do the center of mass, but I would suggest doing the bottom of the ladder. See this force right here? We're going to analyze it around the bottom. Why? Because then how much torque does static friction apply? That's right, none around this point, because it acts through the axis of rotation. If F and R are parallel, there is no torque. Pulling straight out on a door doesn't rotate the door. And the force from the ground also doesn't act, so we don't even have to use that one. We're actually getting rid of two forces here, which makes the problem a lot easier. So that means by making that choice, the only two torques we have left is gravity, which would be positive because it's counterclockwise, and the wall, which would be negative because it's clockwise, but since there's only two of them, they've got to balance for the net torque to be 0. And now it's just about figuring out what the torques are. Well, remember that each torque is R times F. Okay? But the question then is, what's R? Okay, well, for the wall, here's R. And look at that again. I'm putting it on both diagrams, right? R is the distance from the axis of rotation to the point of application of the force. Well, there's an angle in here, right? I mean, we could do the trig, but we can do something easier than that. Remember that one of the ways we defined torque was as the perpendicular R times the force. That's the way we did it in the original lab, right? Well, if the wall is, the force from the wall is horizontal, then the perpendicular part of R would be the part of R that's vertical. And if you look over here, that would be that side. So r perpendicular in this case is actually h. You with me there? The perpendicular part of r, the part of r that's perpendicular to the force exerted by the wall, is h. So the torque from the wall is h times the force from the wall. Now, in a similar way, we could look at r for the force of gravity. That would be from here to here. Well, notice the force of gravity is vertical. So the perpendicular part of r would be horizontal. That would be this side. How big is that side? Well, this gets a little complex here. Notice that this entire side is A. And notice that the center of mass is 1/3 of the way up. So if this whole side is A, what's this side? That's right, it's 1/3 of A. If you want to be technical with your geometry, if you drop a vertical in here, all right, this little right triangle and this big right triangle are similar triangles. They have all three angles congruent, and therefore their sides are proportional. So if this side is A, right, this side's got to be A over 3 because this side is L and this side is L over 3. Ah, yes, similar triangles. So the torque applied by the force of gravity would be A over 3 times the force of gravity. Plug those both in, and of course, force of gravity is our old friend mg. Okay, we get this. Solve, plug all of our numbers in, and we get an answer. 150 newtons for the force of the wall. Now, we could go back, by the way, now and figure out how much static friction there is. 150 newtons. It's not the maximum amount, but it's how much is acting at this point to keep the bottom from sliding out. So again, in all of these pretty complex problems, recognize that the process here is to draw an extended force diagram. There we go. Draw an extended force diagram. Then realize that the net forces are 0. Sometimes those equations are useful. Sometimes we can't actually solve them. But when they are useful, that's great, right? That's just using forces like we've done in the past. And when that doesn't work, you can always write an equation for the net torque, also having to be 0. And when you do that, you can pick your axis of rotation to be convenient. Pick it to get rid of things you don't know, or to get rid of multiple forces, because any force that acts through the axis of rotation exerts no torque. And then it's a problem of figuring out the torques, which is not always a trivial thing. Sometimes you can be geometrically cute like we were here, right, and figure out our answers. So there we go, a couple of pretty complex examples for static equilibrium.